So, first, we're going to look today at horizontal or slant asymptotes. So instead of a vertical asymptote, that dashed line that went up and down, now we're going to have a horizontal dashed line or some sort of slanted dashed line. And these are going to be the same thing as yesterday. They're going to be boundaries again. They're going to be boundaries. Now, to do this, we're going to use the following table. And what you're going to do by the end of the class today is fill in this table here. First scenario is we're going to look at a rational function whose numerator has the same degree as the denominator. Then we're going to look at one where the numerator is less than the denominator. And then finally when the numerator is greater than the denominator by 1. Okay, specifically. So let's start with our first example. What happens when the degree of the numerator is the same as the degree of the denominator? So that's what we're going to start with first. So let's take a look. First, 6x over 3x minus 4. Determine the end behavior. From yesterday, what did end behavior mean? It's on the front page, so you can read it, but tell me in your own words what end behavior means. Ian.
The behavior of a function as x gets larger or smaller.
Good, good. As it gets larger or smaller, that's what I wanted to hear. So we're looking at saying, what happens to the actual function as x gets big, 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 as it gets small, 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 but in negative and positive direction, not towards 0. So, what I did was I started by looking at a table. Take a look at the table here. What's happening to x? It's getting bigger. It went from 10 to 50 to 100. What's happening to the value of the function? It's getting closer to what number? It's getting closer to 2. It is getting smaller, Joe, so you might want to say 0 at first. But what you're going to notice is that if you look at the second table now, you can see that they're going to 2, right? So as the number gets smaller and smaller and smaller, it's also going to 2. So this number is getting closer and closer to 2. See that? Closer to 2. Closer and closer to 2. So we have the end behavior means that it's going toward 2. Okay? It's going toward 2. So look at the graph now. Take a look at the graph. What do you see is happening? Where's the horizontal asymptote located on this graph? At 2. Because it's going toward 2. It's going toward 2. So we have a horizontal asymptote and its equation is y equals 2. Okay? It's y equals 2. You know, another way of thinking about this is down here. Let's take a look at the alternate approach.
So the only way you can find the horizontal asymptote is...
No. We're not going to make a table. Well, I'll show you. We'll look at some rules.
So
we'll come up.
The way you did this one is what you have to look at the table.
Yeah, that's how we discovered it originally, by looking at values. But you can come up with correlations now that are easier, which is what we're going to do. Okay? What I'm doing now, you would use every time from this point on. So what we think about is this. What are we trying to figure out? We're trying to figure out the value of the function when x is what?
Smaller than infinity.
Which is what numbers? Infinity or? Negative infinity. So take a look at these. Read this to yourself and see if it makes sense. Read it to yourself. Since. Read that to yourself and see if it makes sense to you. And then look at the next line and see the difference. See the difference that I made. What did I do? What did I drop off? The negative 4, right, Joe? Ryan, if you weigh 170 pounds and today you lose 1/1,000,000th of a pound, do you care? Honestly? It's insignificant, right? Wouldn't you agree? It's negligible. That's what this is, really. I know you don't care either way, Ryan, but I'm saying if you say you're on a diet and you lost 1/1,000,000th of a pound, are you going to be like, woo! 1/1,000,000th of a pound and I'm good. You're not going to do that, right? No. But it doesn't make sense, right? You would never do that. But the idea is the same here. If you have 3 infinities, is minusing 4 or subtracting 4 going to have any significance at all? So in your mind, think of it as negligible. So when you end up with this 6 infinities over 3 infinities, think of infinity, again, this is not mathematically sound. But think about it as like infinities over infinities. What happens to the infinities? The infinities cancel. No 2 infinities. The infinities cancel out, leaving you 6 over 3. You see that? 6 over 3?
Use 6 infinities for 3 infinities.
You can't, that's the idea. So I'm saying think of infinity as an entity or a variable. But where did the 6 over 3 come from? Go back to the original, people. Go back to the original. Where is 6 and 3 in this equation? Where are they?
X.
They are your what? What is the term? They're next to x, but what are they?
Quotients. I know the variable.
Is it like one we learned?
It is one you learn. Raise your hand, because I can't hear you. You're talking too much.
I know it, but I can't say it. Yeah. And it's like
LC.
Least common denominator.
No,
Least
it's
common
not
multiple. Least common factor. Least common friend.
What does the 3 and the 6, what are they called? They're the what?
Least common
Leading
Least common
Coconuts.
coefficients. Good, Julia. They're the leading coefficients. So here's our rule. Simple. It's very simple. When the degree of the top is the same as the bottom, look at the ratio of the leading coefficients. What's 6 over 3? It's just 2. That's what we got as our answer. 2.
But they're not the same.
Doesn't matter. Doesn't matter what's left after. If the degrees are the same, we're good to go. If the degrees are the same. The degrees are both 1.
X to the first.
X to the first. X to the first. They're both 1. Okay? So you could already fill in this table right here and say this. The end behavior is a horizontal asymptote that's equal to y equals the leading coefficient of the numerator over the leading coefficient of the denominator. Okay? That's what it's always going to be. Always, always, always. Okay, let's do another example. I know, sorry about that. Let's do another example. And in that example, I want to do another method to show the same thing. But the same thing we're going to show, but using another method. Joe, put your desk down. All right. Example 2. Example 2. You guys are welcome to come up with the answer right away just by looking at it, okay? You can do that. That's fine. But what I want to do is show you a different method to show this as well. Take a look at this problem. Ryan, what are the degrees of the numerator and denominator?
X squared.
So what's the degree? 2. So if the degrees are the same, what's the answer right away?
1, 2 over 8.
2 over 8.
Word.
It's the ratio of the leading coefficients, right? 2 over 8. 1 over 4.
So I
Okay?
feel like what if there's a 2x squared plus 4x plus 4 over 8x squared plus 5x?
Still 2 over 8. Isn't that crazy? Doesn't change the problem. Only leading
So like
coefficient.
the biggest coefficient, that's what leading is?
Leading coefficient is the term that's in front of the highest degree.
Highest degree.
Yeah. Now, another way to do this though, and this is what you're going to learn in calculus, I want you to see it. You don't have to do it though, but just to see it. You take the highest degree and divide by that. So look, take the numerator and divide by the highest degree. Take the denominator and divide by the highest degree. What happens? The x squareds cancel, leaving behind a 2, and you're left with plus 4 over x squared here. In the bottom, the x squareds cancel, leaving behind the 8. 5x over x squared is just 5 over x. One of those cancels. And then the negative 3 over x squared is negative 3 over x squared. And at this point in time, here's what I want to do this, and here's the reason. I want you to see something. If you take a look at this answer now, right here. Take a look at this answer right here.
That's your effort. That's your mind.
Okay? Well, it looks like it is, but we want to know the end behavior as x goes to infinity. So plug in infinity.
It's 2 plus 4 over infinity squared. 8 plus 5 over infinity minus...
Hold on. Why are you confused? We haven't done anything that's like confusing. I'm just saying, like, I don't mean to be mean. I mean, like, all we've done is divided by x squared. Do you understand that part?
Where are you dividing by x squared? Both the numerator.
All of the terms get divided. But you have to go back to the basics. A monomial into a polynomial needs to go into each of them. Okay? So we're dividing into each of these and you're getting this right here. So now with this equation though, Ian, we're saying to ourselves, we want to know the end behavior. So plug in infinity or negative infinity.
It's infinity squared.
Well, that's the question now. Take a look down here. What do you do with all these infinities?
Infinity.
And don't look at the answer because it's on the next line, the answer. Don't look. But think for a second. Take a number. Pick a number between 1 and 10.
6, 7, 1,
2.
1.
Let's go with 6. I heard 6. Divide 6 by 1. What do you get?
6.
6. Divide 6 by 3, what do you get?
2.
Divide 6 by 6, what do you get?
1.
Divide 6 by 12.
1/2.
Divide 6 by 18.
1/3.
Divide 6 by 24. So as the number you're dividing by gets bigger, what happens to the overall quotient?
It's smaller.
So you divide by infinity. It's going to keep getting smaller, 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 smaller until it gets to
0.
So all of those terms that are being divided by infinity drop off. What are you left with when they drop off?
2/8.
Which is what, Joe?
2/8, our answer.
Our answer from before. Anything over infinity is going to drop off because anything divided by infinity is really 0. Okay, it's really 0. Write that down. Any number over infinity is 0. Jared.
Is it 0 because the number you divide by is so large it's negligent?
Exactly. That's a perfect way to think about it, yep? The perfect way to think about it. There's another rule you'll learn, or another way to think about it in pre-calc, and I'm going to hold off until then. So again, they're always negligible, leaving behind 2/8. Now, I want to show you an example though. And this is a very interesting example. You need to really make sure you heed this advice or listen carefully. A vertical asymptote from last class, or a hole, cannot be crossed because it was a domain error. Do you remember that? It was what was not in the domain that gave us the vertical asymptote or the hole from last class. The quantities that made the denominator 0. But a horizontal asymptote is not that. A horizontal asymptote is not what makes the denominator 0. So you can cross a horizontal asymptote. So look at the graph here. Look at this specific location right here. Everybody see that? It crosses the horizontal asymptote. And that can happen. An example of that is this. When your car hits a speed bump, the oscillatory motion of the car looks like this. Vibrational, back and forth. That's what's happening. You hit a speed bump, what happens? Your car does this for a little bit, right? But then it settles out. Everybody? Yes? Okay, I mean this is obvious, okay? So, the asymptote here is whatever it's going toward. What is it going toward? What line is this? What line is this?
I know.
The x-axis, which is the line y equals 0. So yes, it'll teeter out. That's because in physics we have dampening forces and friction that'll make that happen. Okay? But it is getting asymptotically closer. Okay?
So if it had no gravity or anything, would it go on forever?
It would go on forever with the same amplitude. It wouldn't even diminish at all. Yeah. And that would have no asymptote. That would be called a periodic function. Periodic.
Jumping up and just keep going up forever.
Yeah, it would also be like if you let go of a spring and the spring goes on forever. When there's no friction, that's what would happen.
The thing is that if you shoot in the top and it just goes on forever.
Is that what would happen like in back?
Yeah, exactly, because of inertia. In space, if you kick an object, it'll go on forever. Okay, unless it gets pulled into a gravitational field. Seriously?
Gravity.
If it gets within a gravitational field of a massive object, it will get pulled into. Alright, so guys, the idea is this. The horizontal asymptote in this problem was 0.25, right? Look at the graph, please. Where do you see? There it is. 0.25. The horizontal asymptote is right there at about 0.25. And you notice the end behavior happens to be the same on both sides. That is not always the case. It's not always the case. Okay? There are exceptions to this. So I don't want you to think that always happens. Let's look at the second case now. Second case, when the degree of the numerator is less than that of the denominator. Okay? Second case. So the first case was when they were equal to each other. Second case is when the degree of the numerator is less than the denominator. So, think about plugging in infinity. What happens? Just look and read off the board. It's right there in front of you. What's happening here? Yeah, you're going to end up with 4 over infinity because that -1 means nothing. It's negligible. Okay? So what do you get when you divide by infinity though? Always.
0.
So whenever this happens, always, it's going to be a horizontal asymptote of the line y equals 0. Always, always, always. Whenever the degree of the numerator is less than the denominator, you have a horizontal asymptote, and the asymptote is y equals 0, which is really the x-axis. You can write that down. Y equals 0 is really the x-axis. Ryan.
What's it called? What happens if infinity over quantity?
What happens if it's infinity over a quantity? Keep doing this.
Infinity minus 1, can you add to it?
Sure, but it's still infinity.
How would you do it?
It's still infinity.
Yeah, that's what I was trying to figure out.
Take one away from the biggest number possible. Well, it's one less than that, but it's still the biggest number possible. Like, you know, theoretically, the idea there.
Well, no, it's not.
Well, less than the biggest.
It's not the biggest number possible. It's the one less than the biggest.
But what is the biggest number possible anyway? But we don't know. It's a theory. So the next number lower is still the same number.
Is it?
If you find this interesting, and which I did in college, there's classes on this, which are called orders of magnitude. And you take orders of magnitude, like, what's bigger, infinity or infinity squared?
Okay.
Right? Technically, you'd think infinity squared is, right? Because it's squared. But in reality, it's like, well, infinity is the biggest number anyway, so how could you get any bigger anyhow?
It's so hypothetical though.
But that's like a theoretical calculus. You know who loves that? You know who likes this? Miss Starks did a math major in theoretical calculus. That was her major. I did applied physics and applied engineering. She did more theoretical, where they talked about that kind of stuff.
I heard so.
Okay? All right, let's look at example 4. Let's look at example 4. Alternate way to solve this besides using our rule. The answer is 0, obviously, because the degree of the numerator is less than the degree of the denominator. So the answer is the horizontal asymptote at y equals 0. Okay? By the way, fill in that table. Make sure you're filling in that table. Here you have a horizontal asymptote, and it's y equals 0. And write down that as the x-axis, please. An alternate way to do this is the same way we did the other one alternately. Divide by the highest degree. Go ahead and divide by the highest degree in the top and the bottom.
Highest degree.
I'm sorry, not the highest degree, the lowest degree here. Jeez.
Why the lowest degree?
Because we want to get the numerator to have a constant in it. So we look at it's the highest degree of the numerator, which in this case happens to be the lowest degree. Okay? So let me rephrase that,
So
sorry.
it's just whatever degree comes up in both.
No, it's the degree of the numerator, the highest degree of the numerator. Okay?
I don't like this infinity stuff.
So the highest degree of the numerator is x to the first. So let's divide by x to the first, leaving the numerator be negative 5. The denominator, when each of these individually are divided by x, this becomes x, this becomes just 4, this becomes negative 2 over x. Now if you plug in infinity, what happens to this when you have 2 over infinity right here?
0.
0, so that drops off. So you now have negative 5 over infinity plus 4. But anything over infinity is 0, so you still end up with 0. So our conclusion is y equals 0. But I want you to see it this way, because in a minute we're going to have an example that does have infinity in the denominator, but the numerator might have like infinity squared, and then it's not going to work that way. Okay? All right.
What are real life applications of infinity?
Oh, infinity?
Usually this.
Oh, all over the place. Anything. Oh, yeah.
Anything? Going to the store. Coming out.
For real. If you're thinking about like the time it would take a train to get to a certain location, if it was
They have maps for that though.
yeah, but if you have to like be the person that does all this stuff, guys, you think they have it? They have it? No, they don't have it. People have come up with it. Those people are called engineers. They come up with it.
Well, let me go and get an engineer.
Then maybe you won't use as much infinity notation, but you know what you use is in stocks. Look at the trend of stocks over a given period of time. As the time extends further. Joe, you could ask this in any class. I could go to my English teacher and say, what if I don't want to be an English major? Then you're not going to use it as much. Sure. So you can say that all day long. But in math and science, in the world of math and science, in the world around you, this is very useful. Maybe if you choose not to do anything with math or science, sure, then it wouldn't be. But that's the same as me saying, I don't plan on speaking Italian ever again, so having learned Italian is useless. It's the same thing, Joe. It depends on what you're going to do. So in the case of what it comes to math and science, there are tons. Infinity notation, all of calculus is based on the notion of infinity. All of calculus, I'm serious. Limits and infinity, those two things, and you haven't learned limits yet, you kind of have. With asymptotes, you've kind of learned it, okay? No way. Waste of your time. Take calculus. Okay? Now,
What is this agreement?
let's keep talking. So, no tangents right now. So this example, the numerator is greater than the denominator in degree by 1. And we're only going to look at examples where it's greater by 1. We can do examples by 2 and I can show you, but I'm not going to do it here. Okay? You're welcome to ask me and I'm happy to show you. You get different kinds of asymptotes. Instead of slant asymptotes, you get parabolic and cubic asymptotes, which are weird, but they actually are, they're not as useful. They're not as useful, not nearly. So for this example, if we try our normal notation and plug in infinity, what's the problem here? Take a look. If you plug in infinity, you're going to end up with infinity squared over infinity, which if reduced becomes infinity, even though mathematically that's not sound.
Is infinity over infinity just 1?
Infinity over infinity,
Yes,
sure.
infinity.
But this infinity squared over infinity.
Is infinity squared, like, it's already based
Again, not mathematically sound. Just stay with me. If you did negative infinity, and you think of this as all variables, you end up with infinity squared over negative infinity. Because this is positive, right? When you square negative. So you end up with a positive or negative infinity. So this tells me, take a look, that the graph, as I go toward infinity, the y value keeps going toward infinity. So as I go to the right, this graph is going to go off like that, toward infinity. As I go to the left, the graph is going to go down. So like that. What does that look like to you?
A line.
A line, thank you. A normal graph. A line, let's use our words, right? Okay, it looks like a line.
Straight line.
That's fine, we said a normal graph. So it looks like a line, right? It looks like a line. So in a minute, we're going to talk about now how this is our, guys, this is our example now of where the slant asymptote is going to come into play. Okay, where the slant asymptote is going to come into play. And to determine what the slant asymptote is, we can use long division. Or we can use synthetic division. And simply look at what's left. So, where's the original? Oh, it's off the board. That's where it is. The original told us the following. If you divide x squared plus 3x minus 4 by x plus 1, either using long division or using synthetic division, look at the portion that's left over. So use synthetic. And take a look at that table. Make sure it makes sense to you. With synthetic division, you take and divide by x minus c. So it's x plus 1, so we put a negative 1 out here. We put our coefficients 1, 3, negative 4 across the top. We divide. Bring down the 1, multiply, add, multiply, add. Here's what you're left with. You're left with x from the 1 here. Remember, the degree of the starting value is squared. So the degree of the answer is going to be linear. So this is x. This is your constant plus 2. This is your remainder. So minus 6 over x plus 1. The interesting part is this. As x gets bigger, because we're doing end behavior, right? As x becomes infinity, what's going to happen to 6 over infinity plus 1?
0.
Becomes 0. So you could cross that off now. What are you left with?
X was 2.
That is the asymptote. Whoa. That is the asymptote. And take a look. If you graph this function, the function is the curved parts. Take a look at these curved parts on the right here. The asymptote is that dashed line that goes through x plus 2. The function fits perfectly on that slant asymptote.
So the whole way up is on like right on.
It's gonna ride along. It's never gonna touch it because it's an asymptote. Okay. A horizontal asymptote you can cross. Remember we talked about?
Yeah.
But this kind of an asymptote is one where it's gonna get closer and closer and not touch.
So because like isotope is like radioactive and asymptote, so you can't touch it.
Oh, interesting. And an isotope, a radioactive isotope has a half-life, which is like that example yesterday we weren't here for. We walked halfway to the door and halfway to the door. That's what a half-life is. It never goes away. Radioactive isotopes never actually go away.
Never get half.
Right.
Why does the remainder cancel off?
Because x goes to infinity, so the denominator becomes infinitely large as x approaches infinity, becoming 0.
So then
Becoming
why
negligible.
does that x go away?
It doesn't go away. This becomes 1 over time. If you plug in infinity, what does it become? Which is where the graph is going. This graph is going up toward infinity. And if you plug in negative infinity, what does this become? Negative infinity. This part of the graph is going toward negative infinity. So our conclusion is that if the degree of the numerator is 1 larger than the degree of the denominator, then the graph has a slant asymptote. It can be cubic up top and quadratic down below. It can be to the fourth power up top and to the third power down below. In those instances, Ryan, listen. In those instances, when it's a cubic over a quadratic, you need to use long division. You cannot use synthetic. You can only use synthetic when the denominator is a binomial. When this denominator here is a binomial, it's the only time you use synthetic. If this were squared and this were cubed, you got to use long division to get the asymptote. Okay, there's 2 videos that you're welcome to watch if you need, or 3 if you need more assistance on this. What I want you to start, you have 5 minutes. It shouldn't take you long at all. Use the table that we filled in here on the next page.
Oh, you filled it in for us.
Oh, how nice, man. Okay, use this table and work on these exercises. I think there's 8 total or 6.
We do here.
Okay, again, separate paper. I want all these on separate paper. I know it looks like there's a lot of room there, but later on you're going to run out of room on the other examples. So do this in your notebook, please. Do this in your notebook. Just put section 2 exercises. Jared.
Can you have a horizontal or slant isotope without a vertical?
You can have combinations of any of them, really. You're never going to have a horizontal and a slant at the same time, simply because of the rules we just went over. If the degree of the numerator is greater than the degree of the denominator, it's going to be a slant asymptote. You can't be horizontal. The horizontal only comes from those other 2 cases. So you either have a horizontal or a slant. But you can have that with a vertical or without a vertical. Okay?
I just gave you to go 1 or 2 or 3.
Yeah, but as long as you know what they mean. Degree is this, degree is this. No, here's what you're going to do. Ready? Watch. For the first one. I would say this. The degree of the numerator equals the degree of the denominator. Right? This is your work to verify. Therefore, y equals 3 over 9, which is just 1/3. Okay? That's what I would do. And I would show a little sketch of the graph and show y equals 1/3 on a graph like this. And then look at the graph it in your calculator, and show what this graph looks like.
So we do the asymptote, we graph the asymptote and the graph.
So just graph the asymptote and graph the graph. You can also plot the vertical asymptote by this point now. The vertical asymptote will be -4/9.
Do we have to find that?
No, but you're going to see it on the graph up here. You're going to see it like this. That's what you're going to see when you graph this. And then you're going to see the curves that bound it. The vertical asymptote was from yesterday, guys. This is the vertical asymptote. When you set the denominator equal to 0, you're going to get -4/9.
Calculated on a certain function?
No. When you say your denominator equal to 0, you're going to get -4/9. That's this vertical asymptote here. When you look at the end behavior, you notice the degree of the numerator equals the degree of the denominator. So you look at the leading coefficients, which are 3 over 9. Y equals 1/3 is this horizontal asymptote. So if I were to label these, here's my labels, which you're going to have to do. So x equals -4/9 is that vertical part, and the horizontal part is y equals 1/3. And you can use your calculator to give you the rest of the sketch. We'll talk more about intercepts and zeros in a little bit.
Number 2 is 0, right?
Number 2, it goes to y equals 0, yep. But I want you to graph it. Go to your graphing calculator, give me a sketch to show me an example of what that actually looks like. So if, for example, I'm going to draw it up here, so take a look. If, for example, here, we've got, let's say, the equation 1 over x. The graph of 1 over x is asymptotic to the x-axis like this. But you can clearly see this is your asymptote. So draw a dashed line over the x-axis showing that that's the asymptote. Okay, so this is y equals 1 over x. It's not one of your homework. Okay, but that's what it would look like. This is what I want to see.
Wait, instead of drawing that line on the x-axis, can we just say y equals 0?
Do both. Put the dashed line and label it as y equals 0.
So I draw a dashed line and solid line.
You have to draw a solid line and maybe use a pen or right above it. Just infinitesimally small above it.
Wait, is this number 2?
Okay. That should be number 2, yeah. Yep. Where are the vertical asymptotes there? They're at plus or minus radical 5. Look at the denominator. What was the denominator of that question?
X squared minus 9.
Oh, 9, sorry. So if you solve that, you get plus or minus 3, right?
Sure.
No, don't share me. Think about it. Look at the denominator. Add 9, take the square root. Plus or
Oh, yeah,
minus
yeah.
3, right?
Yeah.
Don't you notice the vertical asymptotes? That plus or minus 3?
Okay.
That's them. Okay? So you can use last night's and tonight's now. We're building on this stuff. Tomorrow we're going to talk about y-intercepts and zeros of a function. And the zeros of the function are the parts that are going to tell us about the roots, right? The roots of the equation.
What exactly, are you asking for us to draw the asymptote and the graph?
Yes. Now go to your y equals. For those that weren't here yesterday, you need to put parentheses around the numerator and the denominator fully. Finish tonight. We'll talk about this more tomorrow. In your calculator, don't forget parentheses around the whole numerator and the whole denominator, because you're dividing two quantities.
Oh, we don't